Alright everyone, it is our last unit video guide, so it's kind of exciting. We'll get started on those FRQs afterwards. But here we go. So comparing two populations or groups, that is the goal. So first we have a conditions question, and we're trying to do a proportion comparison. When you compare proportions, again, you need at least 10 successes and 10 failures in each of the two proportion groups, right? They also need to be considered independent. It's true. And we also need to take separate random samples of men and women. That's the whole idea. If you take one sample and separate it into men and women, you can't call that a two-sample comparison. So that's the difference. I mean, if I say I'm going to randomly select 100 people, I'm not guaranteed to get 50 men and 50 women and compare them. In this kind of scenario, typically what you want to do is say, okay, let me sample 50 men and 50 women, and then we'll compare the characteristics of heart disease in those 50-50. So just make sure that that's what you're doing if it's a two samples interval. You need separate samples of men and a separate sample of women. Again, you need the independence condition and at least 10 successes and failures. Right? So up next, this is a proportion question where it looks like the confidence interval has already been formed to compare. Let's read here. Now see, just a note on the AP exam, you always need to define P of N and P of S. And right now, if I just look at this, I'm not sure what that means. Let's see, I can now see we're comparing the tax support in the northern samples and the tax support in the southern samples. Okay, so let's break down what this interval is saying. If I have 0.1 minus 0.12 or 0.1 plus or 0.1 plus, then we're looking at this. Our interval is anywhere from negative 0.02 to positive 0.22. So anywhere in between there could, with 95% confidence, be the true difference in proportion. Now what that means is there's a chance that P of S is larger than P of N. That's how you get a negative. Or there's a chance that P of N is larger than P of S, because if it's larger, then you'll have a positive value. Now again, here's one thing that I recently learned on an FRQ. Just because it looks like it's more positive doesn't mean that that's more likely. Each of these are equally likely. Anything in this range, anywhere from the negative 0.02 to the positive 0.0222, is likely. So anyways, what does this mean if we're testing the hypotheses that we think they're not equal? Well, what that means is we're 95% likely that they could be equal because zero's in this interval. If they're equal, then you just get 0 when you subtract them. So if you're trying to conclude that they're not equal, when you have with 95% confidence that it could be equal, then at alpha 0.05, again, what that means is kind of notice 95 is 1 minus 0.05. If 0 falls in that interval, you can't go with HA. There's not enough evidence. So that means the p-value is greater than 0.05, and the p-value is greater, that's when you don't reject. So we can't conclude there's a difference. Again, essentially because when you pass from negatives to positive, that really means zero's in the interval. Because zero's in the interval, you can't conclude that they are different, right? Because 0 means they're the same. And again, it's 95 and 05, so those two will always be related like that. If it's like 95 and they give you alpha 0.1, you can't do anything with that. But when it's this like this and this makes it 100, if 0's in the interval, you can't conclude there's a difference. Right? Up next, this time they're asking me to find the p-value. Okay, now I'm going to run through how to do this by hand, even though I really don't want to for sake of time. Let's make this a two-part video. First, we need to just find the proportion for US. That is, I'm trying to find sorry, 1 minute. Okay, so we're trying to compare the yes diagnosis. So that's 40 out of 200. What is 40 out of 200? Actually, I should write it Again, if you're going to use your calculator in statistics, write all of that down on paper first. So we have 0.2, and then we have the sample proportion from Mexico. That's 20 out of 200. I know what that is. That's just 0.1. Okay, now when you do a proportion comparison test, you need this thing that we call p hat of c. That's why I have my reference sheet here. P hat of c, here we go. It was the number of successes, and we can see those here. We have the 40 plus the 20 over the sample sizes, the 200 plus the 200. Well, that's 60 out of 400, which is 0.15. Okay, so notice that this is what we use for the standard deviation, essentially. It's a part of the standard deviation. So how do we calculate the z-value? We calculate the z-value by saying, let's go in the correct order. Okay, it's US minus Mexico. That's 0.2 minus 0.1 minus the suspected that they're equal, 0. So we assume the different, whatever we get here is going to be compared to just getting 0, that they're the same. We're going to divide that by the standard deviation, and the standard deviation is based on this P of C here, so we have the 0.15 times 1 minus 0.15, which would be 0.85, times, be careful that you use parentheses here, 1 over 200 plus 1 over 200. 1 over the sample size of the first, 1 over the sample size of the second. Let's figure out the z-value, then we'll figure out the p-value. 0.2 minus 0.1 minus 0 is really just, well, there's that. And that whole thing, make sure you press enter on this first, is being divided by the big square root of 0.15 times 0.85 times parentheses 1 over 200 plus 1 over 200. And so we get a z-value of 2.80. Okay, now we're testing greater than. So we're finding the chances of, we already have a positive z-score. We got 2.8. We're finding the odds that it's greater than. So how much area is to the right? Well, if we're at 2.80, there's 0.9974 to the left. Notice the shaded region is for the left. So if we want to find out how much is on the right, we take that amount, the 0.9974, oops, and we do 1 minus that, and we'll find out how much area is remaining above, so 0.0026. Okay, all in all, I now know the p-value. It is less than 0.01, so we would be rejecting. Now, just for sake of argument, let's say you have a graphing calculator. How much easier could this whole process have been? Although this is the work you want to show on the FRQ anyways, how can you be sure of your answer beforehand? Oops. Stat tests, 2-prob z test. Here we go. Oops, not z interval, 2-prob z test. Now x1, 1 was for the US, oops, sorry. So that was 40 out of 200. Then we had 20 out of 200, and we were testing that it was greater than. Calculate, and see, look, 2.800, there's the p-value that does round to 0.0026. There's our p1 hat, there's our p2 hat, and there is actually our p of c right there as well. So you can know ahead of time everything you should get relatively quickly, and then you're just showing the work of how you got it to verify that you know what's going on. Okay, so this is the same setup. Essentially, they're just asking me to do this in order, and I notice it's A minus B, so you should see 50 over 1,000, which is 0.05 first. So it's definitely either this answer choice, or this answer choice. Up next, remember that we need P of C, so we essentially need 60 out of 2,000. I'm skipping over that, hopefully you see where I'm getting that from. The S and the S over the 1,000 over the 1,000. So 0.03. Okay, so in other words, I should see 0.05 minus 0.01, and I should see my denominator based on P of C. So it looks like this is correct. Oh wait, no it's not, because it's over each individual sample size, which was 1,000 to 1,000. So this is our correct answer choice. So read through that again. I'm just trying to save some time and speed up, because somehow I've already taken up 10 minutes. I mean, two-proportion comparison does take a while, and I'm trying to be a little thorough. Okay, this time they want a 95% confidence interval, and we're comparing means. So let's do that. So we're doing b minus n. So the way we're going to compare that is first we're just going to get x bar of b minus x bar of n plus or minus our critical t value, and we're going to use what we call the conservative degree of freedom along with 95%. I'll explain what that means. And then we multiply that by the square root of, and we can see it on our reference sheet. We use the first standard deviation squared, in other words, the x of b squared over its sample size, plus the second one over its sample size. Okay, so that would be s of b squared over nb plus s of n squared over n. Okay, let's start filling this whole thing out. So what is the sample mean that we got from b? Let's see here. So badges was an average of 12. Just going to kind of fill things in where I can here. And they said the standard deviation was 26. So 26 squared. Does it say how much each sample size was? So 30 in each sample. Okay, so what does conservative degrees of freedom mean? It means degrees of freedom based on the smaller sample size. Well, this time they're both 30. So smaller doesn't matter. We're just going to use 30 as our n to calculate our degrees of freedom. Okay, the other one without badges was 8. And then we have its standard deviation, which was 21 squared over, and they both had a sample size of 30, so 30 and 30. Now let's find what I mean by conservative degrees of freedom in 95. So I'm looking for, first, on the t values, because this is a mean comparison, 95% confidence. Now conservative means find the smaller sample size, well, 30 either way. So degrees of freedom is always n minus 1, so we're looking at 95% confidence with 29 degrees of freedom. That t-value is 2.045. If you use the calculator, it's going to use a different degrees of freedom value. It won't be too far off, you'll still be able to get it right, but it will be a little bit different. Okay, so now let's calculate this whole thing. I'm going to do it like this. I'm going to do 12 minus 8 plus 2.045 times big square root of 26 squared divided by 30 plus 21 squared, squared divided by 30. I get that. Now that's my upper bound because I added, I copied the whole thing in, and that was the upper bound. Now I'm going to go back and change this to a minus. All right, don't redo all your work, and I get this. Okay, so it looks like my correct answer is right here. Now just to show you, again, your calculator can do this if you do have one. If we go to stat tests and we want a two-sample t interval, you're always going to input the data as stats. You don't have the raw data. Our first was the 12, and that standard deviation was 26. Oops, sorry. Oh no. Okay, 12, 26, and the sample size was 30. Then we had 8, and then we had 21, and the sample size was 30. And we're doing confidence level 95. Pooled should always be set to no, and we calculate. Now, we're probably going to see a little bit of a difference in degrees of freedom. See, definitely a big difference there. However, look at our interval. If you compare all of our answer choices, it's still very close to answer choice B. So all I want to make a point of here is if you're doing the FRQs on the exam and you're using your calculator, make a note that you were using the calculator to find the interval, and that's going to account for the slight difference in the answers of doing raw by hand or doing calculator. Both are totally correct. Both are almost the same. Just specify which way you went about it. I mean, obviously, if you went by hand, you're going to see that. But if you say I used my TI-84 and I used, if you're going to say you used your TI-84, make sure you explicitly write, XB was 12, S of B was 26, and N of B was 30, and all that stuff, and then say input into TI-84, two sample t interval, and then just write down your answer, and you're done. Okay, I'm going to cut this video off, and we'll do part 2. Sorry it's taking so long, but hopefully you're enjoying